Good morning, everyone. My name is Dr. Pritika, Assistant Professor from SRM Institute of Science and Technology. Let's see about tall buildings, a journey quite literally from ground up. We will explore how humanity learned to build not just tall but intelligently tall. The story of tall buildings isn't just about steel and concrete. It's about land, economics, ambition, and engineering ingenuity. From the low-rise neighborhoods many of us grew up in to the super tall skyscrapers. So let's begin. Before we talk about skyscrapers, let's establish and classify the tall buildings. So how do we typically divide them? So we divide them into three categories: low-rise, medium-rise, and high-rise. While we are saying about low-rise buildings, these are the structures with 1 to 3 floors up to 12 meters in height. Think of your neighborhood houses, small shops, or primary schools. They rely on load-bearing walls or simple frames. And here is a practical detail: no elevators needed. Just take the stairs. Second, medium-rise buildings, 4 to 10 floors. It's approximately about 12 to 35 meters. Now we are talking about apartments, complex, mid-size office, hotels. It's mainly made up of reinforced concrete or steel frames. So here we need elevators, absolutely essential. So this is where vertical circulation starts, defining the architecture. Next, high-rise buildings. These are 10 plus floors, that is more than 10 floors, which exceeds 35 meters. These are now called upon skyscrapers. So here we are now in the territory of tubular frames, outriggers, diagrams, and here, while speaking about safety systems like fire suppression, emergency egress, structural redundancy, everything is absolutely essential. So while if a 10-story building is there in a small town, we call it as high-rise building. So what is the need of this? Why do we build tall buildings? Why go through such a complexity? The cost, engineering challenges, why? What is the need of it? So the very first need is land scarcity. It is an obvious and very basic need. While the urban populations grow, they are growing very fast, and we have run out of horizontal space. So at that time, undoubtedly, we need to move up. So building vertically allows us to stack uses like residential, retail, offices above parking, and these minimizes urban sprawl. And critically, it preserves agricultural land on the periphery. Every hectare we don't sprawl is a hectare that can still grow fruit or remain ecologically intact. And secondly, economic catalyst. So tall buildings are fundamentally economic missions. They maximize leasable floor area in high demand, and they become financial hubs, job centers, and they are typically well connected to transit networks. The return on investment for a super tall tower in a business district can be extraordinary. And third one, symbolic identity. This one is fascinating because it's less tangible but equally powerful. They represent technological progress. They enhance global city recognition. They become postcards, movie sets, symbols of national ambition. When Dubai built the Burj Khalifa, it wasn't just building offices and hotels, it was announcing its arrival on world stage. So the need is practical, economic, and symbolic. So all three must align for a tall building project to truly succeed. And next is a very big thing, that is challenges while we are going for tall buildings. If a building is tall or easy, every city will full of Burj Khalifas. But tall buildings face multifaceted challenges that span structural, logistical, and environmental domains. As we hope higher, gravity loads increase. Yes, but literally, loads become the dominant design concern. Wind forces grow with height. Seismic forces create complex dynamic responses, and we have to control sway and vibration to keep occupants comfortable. Logistically, construction itself becomes a marvel. How do you get concrete to the 84 before it sets? How do you manage crane operations in wind? How do you coordinate thousands of workers vertically? The logistics of tall building construction are often as complex as structural design. Environmentally, tall buildings cast shadows, alter wind patterns, add amounts of energy for heating, cooling, and vertical transportation. They create urban heat islands. So, the carbon emitted during construction is very significant. Each of these challenges requires specialized engineering solutions. But throughout the building's operational life, tall buildings are not set and forget structures. They demand continuous attention in it. And given those environmental challenges, sustainability in tall buildings has moved from nice to have to absolutely essential. So there are four key pillars. Energy efficiency. This starts with building envelope, high performance facades, low UV values, double or triple glazing, proper shading. Inside, the LED light and efficient HVAC systems with smart automation controls can reduce energy consumption dramatically. In a tall building, when you are heating and cooling enormous volumes, every percentage point of efficiency matters. And next one, renewable energy. Many modern towers integrate photovoltaic panels, small wind turbines, and geothermal heat pumps offset energy demand. Small wind turbines can work at height where wind speeds are higher. Geothermal heat pumps, where site conditions are low, can handle baseline heating and cooling loads. So these are sometimes on rooftops, sometimes integrated into the facade itself. And and again, water conservation. So tall buildings can harvest rainwater from their large roof areas, and grey water recycling, where treating sink and shower water for reuse in toilets or irrigation. These reduces potable water demand. Low flow fixtures are now standard. And lastly, green certification. That is, these validate all the above. LEED, BREEAM, WELL, these aren't just acronyms on a plaque. They provide frameworks for measuring and improving sustainability and occupant wellness. A well certified building, for instance, doesn't just save energy, it actively promotes the health of the people inside it. The message here is clear. The tallest buildings must also be the smartest buildings. Height without sustainability is no longer justifiable. So, how we classify tall buildings by STBUH? Let's get more precise about how we measure tall. The Council on Tall Buildings and Urban Habitat, founded in 1969 in Chicago, is global authority on this. They define three height measurements. Architectural top is a primary standard. This is the highest point of the building in structural elements, including spires but excluding antennas and functional equipment. Highest occupied floor is a self-explanatory. And tip includes everything like antennas, flagpoles, and other works. Using the architecture's top standard, STBUH classifies buildings into three categories. Tall building, which is roughly about 50 to 150 meters tall, and super tall buildings, they are roughly about 300 meters and above, and mega tall buildings, which is 600 meters and above. To put it in the perspective, the Burj Khalifa, which stands in Dubai at 828 meters to its architectural top, it is by a significant margin the world's tallest building as of now. and it sits in the category mega tall that only a handful of buildings worldwide have achieved. This classification matters because it shapes expectations, codes, and engineering approaches. A mega tall structure isn't just a tall or super tall, it operates in a different engineering regime entirely. And while we are seeing about all these tall buildings, a very basic thing is the loads. Now, let's get into the engineering point of view. What are the loads that a tall building must resist? Gravity loads are the one we all understand easily, that is dead loads. The self weight of the structure, finished fixed equipment, these are permanent. So, and as well along with it, live loads. Live loads are occupants, furniture, mobile equipments. These vary. And then other gravity loads like snow accumulation or ponding water on flat waters. But here's a critical insight of tall buildings. Next one is lateral loads. There is a critical insight. It governs the design. The lateral loads can be divided into wind, seismic, and temperature unsettlement. While wind is the dominant lateral force, it increases with height. Wind speeds at 400 meters are substantially higher than the street level. And wind doesn't just put, it creates complex phenomena like vortex shedding, where alternative vortices create rhythmic perpendicular forces. They can cause dynamic oscillation. We will come back to how we handle this. Seismic loads are inertial forces generated by ground motion. The building wants to stay where it is, but the ground moves and the building resists. In seismic zones, we need ductile systems that are deform and absorb energy without collapsing. Temperature and settlement are often overlooked, but they are also important. Differential thermal expansion between sunny side and shaded side of a tall building can induce stresses. And foundation settlement, differential settlement between columns must be carefully controlled. So tall building design is a balancing act, managing gravity, dominating lateral force, and accommodating environmental effects. And structural systems. Given these loads, what are the structural systems we need to use? So let's see from simple to complex options that are available. So first one is moment resisting frame, best for buildings up to 20 stories. The beams and columns are rigidly connected, so the frame itself resists lateral loads. And the advantage of it is tremendous architectural flexibility, open floor areas, large windows. And what is the limitation here? As you go higher, the sway becomes excessive. So there will not be any lateral stiffness available there. So next one is braced frame. We add diagonal members to create triangulated panels. This gives high stiffness economically. The trade-off, those braces may obstruct openings, windows, doors, separation path. And next, shear wall. It is a solid reinforced concrete walls that carry lateral loads. Very high stiffness, but they restrict floor plan flexibility. You can't put a door through a shear wall. Frame core system, a central concrete core housing elevators, stairs, utilities, works with a perimeter frame. The core handles most lateral loads. The frame carries gravity. Efficient load distribution, but the core itself limits planning at center of the building. And tube system for very tall buildings, 50 stories and above. The perimeter becomes a rigid tube like a hollow box column. This gives high stiffness while keeping interiors open. Fazal Khan pioneered this in 1960s. Complex to construct, but conformation transformative for height. Outrigger and belt stress. For super tall buildings, outriggers connect the central core to perimeter columns at mechanical levels. Belt trusses tie the perimeter together. This system controls lateral drift very effectively, but it requires precise coordination, structural and architectural mechanical. Diagrid, diagonal grids on the exterior, fewer columns needed, often visually striking, but complex fabrication and erection. Hybrid systems combining multiple approaches, optimized performance, but design complexity increases significantly. The choice of system depends on height, function, site constraints, and architectural intent. There is no single best system, only the most appropriate one for the specific challenge. So let's step back and look at how we got here, the global evolution of skyscraper. So United States. Charles started with the home insurance building in Chicago at 1885. This was the first building to use a steel frame, the skeleton that made height possible. Then came the icons, the Empire State Building, the Chrysler Building, Willis Tower, each defined an era. And then Fazlur Khan, a Bangladeshi American structural engineer, revolutionized everything with tube structures in 1960s. Without Khan, we wouldn't have the super talls we see today. Strict preservation laws limited heights in historical city centers, but business district emerges on the periphery. Canary Wharf in London, D'Alevins in Paris, the Shard, completed in 2012, now leads Western Europe at 310 meters. It's notable not just for height, but for sustainable design integration. And Asia, rapid growth. Japan pioneered seismic isolation technologies after devastating earthquakes. China's economic boom produced towers like Shanghai Tower at 632 meters. And Burj Khalifa in Dubai, 828 meters, stands as the world's tallest, a symbol of ambition and engineering prowess. Each region contributed differently. The US gave the structural DNA, the Europe gave us tension between heritage and modernity, Asia gave us the scale and the seismic innovation. Together they created the global skyscraper culture we have today. Wind resistance and racing. I want to close with wind because for every tall buildings, wind is often the ultimate design challenge. Key factors we consider are structural, sorry, strengthness ratio. The taller and thinner a building is, the more it wants to sway. Natural frequency, we must avoid resonance with wind, just frequency. Damping ratio, how oftenly oscillations die out. We often use tune mass dampers or TMDs, enormous weights near the top of the building that counteract sway. Aerodynamic shaping is increasingly important. Tapering the building as it rises, adding setbacks, rounding corners. These aren't just aesthetic choices, they disrupt vortex spreading and reduce wind forces. The Burj Khalifa's distinctive form is heavily driven by wind engineering. For serviceability, we limit drift about 1/500 of the height and we keep occupant acceleration under 15 milligrams. Above that, people start feeling seasick in their offices. And bracing types, commonly we use X bracing, which gives highest stiffness and is economical. And K and V bracing, they allow larger openings. Chevron bracing, which keeps ground floors open. Knee and portal bracing suit low to medium rise buildings. And tension rods or cables or lightweight options, often used in retrofits. So wind isn't just a load to resist, it's a force to dance with. Though shaping, damping and intelligent structures